Building Explainable and Interpretable Model for Diabetes Risk Prediction. Anshuman Guha, Johns Hopkins University Department of Computer Science, Baltimore, Maryland, USA. Abstract: diabetes is becoming a prolific disease and a global pandemic. The capability to detect diabetes early can improve the scope of disease management. For disease prognosis, artificial intelligence techniques are used widely. In this paper, probability and prediction for diabetes are discussed along with its model explainability and interpretability. A UCI repository's new diabetes dataset, which is collected from Bangladesh patients, is used. Various tools were used to interpret the model outcome, like local interpretable model agnostic explanations, LIME, Shapley Additive Explanations, SHAP, tree-based model feature importance, partial dependency plots. A plethora of tree-based and other popular classification algorithms were used to build the diabetes prediction model. The findings indicated that using kernel-PCA before fitting random forest, RF, gives slightly better results than vanilla RF. Our findings indicate a strong positive correlation with the 3 Ps of diabetes, i.e., polyuria, polydipsia, and polyphagia, along with genital thrush, visual blurring, and delayed healing. Being a female in this dataset, derived from Bangladesh patients, have a high chance of diabetes. This represents the model's accuracy and reliability that eventually will be crucial in the trust of medical practitioners on the model outcome. The counterintuitive outcome of individual data attributes was examined with model-agnostic interpretability of machine learning techniques, which can be explained with domain knowledge of the data. The outcome also suggests that the model built on one domain, like population demographics, cannot be directly applied to other demographics. Any patterns observed in the data relevant to the model outcome should be well studied and explained, along with model accuracy metrics. Keywords: diabetes, interpretability, explainability, local interpretable model agnostic explanations, Shapley Additive Explanations, partial dependence plots, TSNE, random forest, decision tree, machine learning. Introduction. Diabetes is emerging as a concerning global health problem that is nearing epidemic proportions globally. According to an estimate of the International Diabetes Federation, the comparative prevalence of diabetes during 2007 was 8% and likely to increase to 7.3% by 2025. The number of people with diabetes is 246 million and likely to increase to 380 million by 2025. 1. The 3 Ps of diabetes is polyuria, polydipsia, and polyphagia. It is common for several symptoms to appear together, i.e., thirst, polydipsia, and an increased need to urinate, polyuria, will often come as a pair. The earlier diagnosis of diabetes would help in better management of the disease. Artificial intelligence has helped make an early diagnosis of diabetes 2-3-4. A robust interpretable model representing a good correlation with cardinal features of diabetes can provide more confidence to medical practitioners and patients in the model prognostics. A better understanding of how an algorithm works can help better align the model outcome with the critical questions required for validation. Amongst a wide variety of machine learning algorithms that were used to predict diabetes, some include the traditional machine learning method 5, linear models, tree-based models and support vector machine. PolydIT. AL6 used principal component analysis with neuroinference for diabetes detection. UET-AL7 used quantum particle swarm optimization algorithm and weighted least squares support vector machine. Rossovy and ET-AL8 implement linear models. Georgia ET-AL9 used multivariate prediction approach and Ojseft and Gulton 10 used futuristic model of rotation forest for diabetes prediction. Alama Muhammad ET-AL, 2019, implemented neural network, tree-based methods, and clustering techniques are used to build prediction models for diabetes. In this study, along with various tree-based and other popular classification algorithms, a wide range of techniques are used to make the model more explainable and interpretable. The focus is to explain the underlying data rather than purely focusing on model prediction accuracy. The paradox of correlation and causation is explored. The random forest model on this dataset already achieves 98% AUROC, so more emphasis is given on investigating the underlying data. The practical relevance of features with the problem statement, i.e., diabetes prediction, is emphasized, and results. W.R.T. to contributing features are explained with wide variety of techniques. Materials and methods. A. Dataset. Sylhet Diabetes Hospital patients in Sylhet, Bangladesh, diabetes dataset is used in this paper, UCI repository 11. The dataset has patients' critical attributes which are helpful for diabetes prediction. The diabetes, PID, dataset having 17 = 16 + 1 features, 328 male patients, 192 female patients and 268 positive instances, 61.5%. The detailed description of all attributes is given in Table 1. B. Maintaining model explainability and interpretability. Interpretability describes the cause and effect that can be observed within a system. Explainability is the extent to which a machine or deep learning system's internal mechanics can be explained in human terms. Interpretability provides the ability to understand the mechanics without necessarily knowing why. Explainability is able quite literally to explain what is happening. Regulated domains like healthcare and finance are dataset description and characteristics. Explainability methods. Shapley plots. SHAP, Shapley Additive Explanations, related game theory with explanations and represents locally accurate additive feature attribution method. 12 For example, in Fig 1, this patient has a very high risk of diabetes with a probability of 0.81. The contributing factors are polyuria yes, age 41 and the top factors which are against having a diabetic patient are polydipsia no, gender male, and alopecia no. Attribute or high value will result in a high probability of diabetes and vice versa for negative coefficient. Further, examining the p-values i.e., less than 0.05, will suggest attributes are important to diabetes prediction. Table 2 exhibits a GLM model output with all variables. The attributes which have statistically significant for diabetes prediction are gender, polyuria, polydipsia, irritability, itching, genital thrush, visual blurring, and delayed healing. Diabetes. The presence of these positive attributes with positive coefficients i.e., polyuria, polydipsia, irritability, genital thrush, visual blurring, and delayed healing, increases the chances of diabetes. Lime plots. LIME, Local Interpretable Model Agnostic Explanations, is used for explaining model outputs and locally approximating the selected model with an interpretable one. The interpretable models are trained on small samples of the original observation. Thus, they only provide an excellent local approximation. The LIME plot presents two contrasting individuals. The first one with no polyuria and polydipsia has a much lower probability of diabetes. The second person has both of these conditions have a 72% chance of diabetes. Further, the counterintuitive fact that having alopecia, hair loss, lowers diabetes can be explained with the fact that hair loss is prominent in aging men in Bangladesh, but they are less prominent in having diabetes. LIME plot, explaining feature contribution to patients with high and low risk probability. D equations random forest and tree-based feature importance. Random forests are practical algorithms for feature ranking, and they use mean decrease impurity is exposed in most random forest libraries. However, the concern arises with correlated features. Robust features can end up with low scores, and the method can be biased towards variables with many categories. Fig 4 depicts the order of features important, contributing to the prediction of diabetes in patients. It is essential to predict which patients have a high propensity to have diabetes, but presenting feature importance would help in early detection. RF feature importance plot. Below, Fig 5 presents the diabetes classification decision tree as a flowchart-like structure where the node represents an attribute, the branch explains a decision rule, and the leaf node presents the outcome. The top node in a decision tree is polydipsia. If a polydipsia and polyuria is true, then 166 out of 170 patients have diabetes. If polydipsia and polyuria are both negative, then 138 out of 170 samples will not have diabetes. This flowchart representation helps us in decision making. It is a visualization like a flowchart diagram that easily mimics human-level thinking. Partial dependence plots. The partial dependence plot presents the marginal effect one feature at a time on the predicted outcome of a model, J. H. Friedman 200,125. The following figures show some example PDPs. Fig 6a and 6b exhibit that both polyuria and polydipsia contribute to a higher risk of diabetes, and being a male in Bangladesh dramatically reduce diabetes chances. Partial dependence plot for polydipsia. Partial dependence plot for polyuria. FPCA and TSNE plots. Both Fig 7 and Fig 8 represent PCA and TSNE, T-distributed stochastic neighbor embedding, representation respectively, and show good separability in the data, which suggests that any classification algorithm will have tremendous accuracy in predicting diabetes in this group of patients. The decision boundary is nonlinear. Therefore, tree-based models will perform well. This often serves a good starting point to visualize the data in two-dimensional space and choose an appropriate classification algorithm. TSNE plots showing good separability between classes. Modeling. A. Covariance, correlation, and Colinerity. Both terms measure the relationship and the dependency between variables. Covariance explains the direction of the relationship between variables, and correlation measures both the strength and direction of the relationship between any two attributes. Correlation is a function of the covariance. The difference between correlation and covariance is the fact that correlation values are standardized, whereas covariance values are not. As described in Fig. 10, both polydipsia and polyuria have a high correlation of 0.6. Therefore, one of these features will be dropped during the modeling stages. Correlation plots between features. Results. A wide range of classification algorithms was used on the diabetes dataset. All algorithms were different, as the underlying mathematical principles for all these algorithms were different. The results were evaluated based on the following metrics. Model and output comparison. Both standard linear PCA and kernel-PCA have been applied for feature reduction and feature space separation between two classes, i.e., diabetes and no diabetes. The feature space is fed into a random forest, RF, model and compared with vanilla RF results. Kernel-PCA extracts nonlinear features space compared to standard PCA. All performance metrics and AUROC for kernel-PCA RF and standard PCA RF are 94.2% and 98.09%, respectively, which surprisingly performs worse than vanilla RF AUROC of 98.4%. The RF algorithm does not suffer from a high number of predictors since it only takes a random subset to build each tree. Support vector machine, SVM, performed well with AUROC of 96.24%. Logistic regression was performed as well, with AUROC of 94.64% on this dataset. Linear discriminant analysis closer to logistic regression results with AUROC of 94.63%. The naive Bayes, NB, classifier performed decently with AUROC of 93.77%. The k-nearest neighbor classification, KNN, performance performed worst with AUROC of 92.12%. Discussion. AUROC performance with kernel-PCA and PCA before feeding the RF model exhibits that PCA does not help better data separability. One caveat is that this phenomenon is highly dependent on data. The reason being that decision trees are sensitive to the rotation of the data since the decision boundary they create is always vertical or horizontal. Therefore, if data is less separable, it will take a much more giant tree to separate these two classes, but if data aligns with its principal components, the perfect separation can be achieved with just one layer. SVM works well in the dataset with a clear margin of separation. Logistic regression performs decently, which suggests a linear separation between the classes in this dataset. For the cases of more complex and nonlinear datasets, linear-based algorithms may not be ideal for classification tasks. KNN is a simple and instance-based nonlinear data. As shown in Table 5, age explains most of the variance in Principal Component 1, PC1. Both polydipsia and polyuria are top differentiating features from the diabetes classification perspective, but explained variability in data due to these features are less due to only two possible values, i.e., 0 and 1. Conclusions. The preferred machine learning techniques are incredibly useful for a diabetes diagnosis. Early prognosis of diabetes would help in patients' treatment. In this paper model, explainability and interpretability are also much emphasized. A new diabetes dataset from the UCI repository, which was collected from Bangladesh patients, is used. Shapley plots explain the extent of attribute impact in diabetes prediction in a positive or negative direction. GLM results help to understand statistically significant features. Line plots explain contrasting risk scores for couple of diabetes patients with contributing features. Partial dependence plots and decision tree explains the directional and quantitative impact of top contributions attributes. Various agnostic tools to interpret machine learning algorithms are used to examine and explain the unusual data behavior. Both PCA and TSNE exhibit good separation of a dataset into two classes, that can be separated using a nonlinear boundary. After that, a wide variety of tree-based and other popular classification algorithms are used to build a diabetes prediction model. The latent space after kernel-PCA and PCA are also used with RF algorithms. The vanilla RF produces the best AUROC of 98.4% after taking a mean of 20 folds. This study's scope can be applied to arthritis, cancer, and other prolonged chronic diseases where early prediction can provide a cure or reverse the condition. Other attributes, including physical activity, ancestral health condition, body weight, and energy levels, can be considered in the future to diagnose diabetes.